of radiation. And damage from high-energy ionizing radiation particularly starts to happen outside the magnetic shield of the Earth. And so that means you're more than about 70,000 kilometers away from Earth. It's obviously a very gradual difference. DNA damage is one of the primary effects, and we have an upcoming mission to look at that. DNA can be broken, cells can die, mutations are possible, and that's one of the things that's a concern for long-term habitation in space. There are other things in extraterrestrial environments if you're not just in a spacecraft, but if you land on the moon or Mars or somewhere else, even an asteroid is being considered. The dust, the environment can chemically do interesting things. And so all of these things can potentially interact with one another, and sometimes they're antagonistic, sometimes they're synergistic. So the why of all of fundamental space biology is certainly human space travel, thinking about perhaps inhabiting the moon with a base someday. Planets are obviously much further off if they're even practical. But also back on Earth, insights and therapies for human disease, for aging. Radiation effect sounds a little esoteric, but many of us, sometime point in our lives, may develop cancer, and radiation is a very common way, still quite effective way to treat many sorts of cancer. And so any of us who has that kind of treatment might be concerned about the biological effects of radiation. So this is simply to say, as we all say in an academic environment, you study basic phenomena, you learn new things, and that informs you and helps you answer lots of questions and problems. So here's some examples of a couple of these CubeSats. These are the 10-centimeter cubes from Cal Polytech in our neck of the woods. This is from the National University in Taiwan. This is GeneSat, the first one we flew, 4.4 kilograms, 3 liters roughly.